You ever just look up and wonder how all this stuff around us actually stays up? I mean, these massive, heavy things just hanging there in what looks like a really delicate balance. Well, today, we're going to pull back the curtain and look at the unseen engineering that literally keeps our world from falling down.
Okay, just look at this thing. It's a Triassic light, right? Weighs, what, 15 kilos? And it's just dangling over a busy street. It honestly looks like it's just hanging by a thread, totally at the mercy of the wind. Just a few thin cables holding it all together.
It feels kind of like a magic trick, doesn't it? But, it's not magic. It's physics. And there's this core principle that lets engineers know with total certainty that this whole setup is completely safe. So, what's the big secret? Well, it all boils down to one single, super important idea.
All right, section 1, hanging by a thread. And really, our journey here starts by just noticing how common this is. Things just suspended in midair all around us. And once you start looking for it, you see it absolutely everywhere. Think about it. A giant concrete slab getting lifted onto a skyscraper, a heavy engine block on chains in a garage, heck, even just a flower pot hanging on a porch. They all have one thing in common. They're held perfectly still. Okay, section 2, the point of balance. Now, to get how these massive things stay put, we've got to zoom in. No, I mean way in. Because the secret isn't in the big picture. It's in one tiny single point where all the forces come together.
Yep, that's it. The key to that whole traffic light system is just one little point, that ring where all the cables meet up. In engineering, we can basically treat that one connection as a single particle. And here's the cool part. If that one tiny point is stable, the whole system is stable. Simple as that.
So this idea, this state of being perfectly stable, it has a name. It's called equilibrium. Now, the textbook definition says a particle is in equilibrium if it's at rest or moving at a constant velocity because the total force on it is zero. In our case, it means all the pushes and pulls on that one point, they just perfectly cancel each other out. The net result? Zero.
But okay, let's translate that from engineer speak. All that really means is a state of perfect balance. That's it. Every single pull in one direction is met by an equal pull in the opposite direction. Nothing is winning. It's a perfect standoff. All right, section 3, making forces visible. So you're probably thinking, okay, but these forces are invisible. How on earth do you work with them? Well, engineers have this brilliant and honestly super simple tool to do just that. It's called a free body diagram. And there's a great little explanation for it, right? Imagine a simple bucket hanging from a cable. The diagram shows just two forces. You've got its weight, which we'll call W, pulling it down, and you've got the tension in the cable, T, pulling it up. For that bucket to just hang there, not moving, T has to equal W. It's not simple. The forces are balanced.
And this is a method you can use every single time. It's 3 simple steps. Step 1, you draw the object by itself, like you've cut it free from everything around it. Step 2, you draw an arrow for every single force acting on that object. Gravity pulling down, cables pulling up, you name it. And step 3, you label those forces. And just like that, you've turned a messy real-world problem into a clean, simple diagram you can actually solve.
Okay, so now we can see the forces. Let's get into the rules of the game. Section 4, a cosmic tug of war.
I want you to picture a classic tug of war. If both teams are pulling with the exact same amount of force, what happens to the rope? Nothing. It stays put. It's in equilibrium. Well, that is exactly what's happening at that little ring holding up the traffic light. It's like a cosmic tug of war where nobody wins. All the cables are pulling in their own directions, but their forces are so perfectly matched that they all cancel out. And this whole tug of war idea gives us 2 incredibly simple but really powerful rules for anything in 2D. First rule, the sum of all the horizontal forces has to be 0. In other words, everything pulling left has to perfectly balance everything pulling right. Second rule, the sum of all the vertical forces is 0. So everything pulling up has to balance everything pulling down. That's it. With just those 2 rules, we can figure out any unknown force we need to. Okay, so let's put this to the test with something a little trickier. We've got this 60-kilogram cylinder. Its weight, of course,
pulls straight down. But notice the cables are pulling at angles. And that's where the free body diagram is our best friend. It lets us break down those diagonal pulls into simple horizontal and vertical parts. So look at this table. For the horizontal or X direction, we've got the forces pulling left versus the forces pulling right. And for the vertical, or Y direction, it's the forces pulling down versus the forces pulling up. We're just sorting everything out so we can make sure it all adds up to 0. So we take these values, we plug them into our two simple balance equations, we do the math, and we get our answer. The tension in that one cable, cable C, is 476 newtons. Now, to put that in perspective, that's like holding up a weight of about 48 kilograms or 107 pounds. And just like that, we know. We know exactly how strong that cable has to be. No more guessing. It's just math.
Okay, but the real world isn't flat, right? It's 3D. So what happens when we add that third dimension? Section 5, adding a third dimension.
And this is the beautiful part. The core idea stays exactly the same. In 2D, we had to balance left and right, and we had to balance up and down. To go to 3D, all we do is add one more pair, front and back. So now, the sum of all the forces in that third direction, the z-axis, also has to equal 0. That's it.
And what's so amazing about this is how beautifully it scales up. With just these 3 simple rules, you can analyze ridiculously complex 3D structures, everything from a hook on the wall to the massive support systems for a bridge. Sure, the equations might get a little bit longer, but the fundamental idea of perfect balance, that never, ever changes.
All right, let's zoom back out for the big picture here. Section 6, the world in equilibrium. So what are the big takeaways here? First, equilibrium just means perfect balance. All forces cancel out. Second, that handy tool, the free body diagram, is what lets us make all those invisible forces visible. Then we learned the simple rules of the game. For 2D, left has to equal right and up has to equal down. For 3D, you just add one more. Front has to equal back. And finally, and this is the most important part, it's this one simple idea, just repeated over and over again, that holds these huge, complex structures together.
So next time you're out and about, maybe you're stopped at a light where you see a crane on the skyline, or heck, even just the chair you're sitting on right now, just take a second. Think about that cosmic tug-of-war happening all around you. All those unseen forces pulling in every direction, held in this perfect invisible balance. It makes you wonder, doesn't it? What unseen forces are holding your world together right now?